I mean, yes.
All right. So yeah, thanks to the organizers.
Sorry, Christian, you have 50 minutes just to let you know. I think we merged the two talks to one.
Yes, okay. Yes. Maybe you can let me know after 45 or something. That would be great.
I will stop you.
Okay, very good. So thanks, Mechthild, for the invitation, and thanks for everybody for being here. Maybe I have to also change the view. Yes. So thanks very much. So I will talk about mean field limits of network dynamics. So this is a topic that's basically at the intersection of graph theory, graph limit dynamics, dynamical systems, and differential equations. And I'm particularly sort of enjoying this interdisciplinary sort of style of the meeting, since there's lots of people from different areas that are represented in my talk here, and also since I'm in Munich, which is relatively close to Austria in some sense, and I still have a sort of external faculty position in Vienna, I particularly enjoy always meetings between the Austrian and the German mathematical societies. So what's the plan for today? So I will try to motivate a little bit where the models and the techniques I'm looking at are coming from, and why I think they are important, and why mathematics really needs to contribute something. So roughly speaking, I will tell you a little bit about classical mean field, and then about something called graphon mean fields. Graphons already appeared in this mini symposium a number of times. And then in the end of the talk, I will build up some sort of more structural view on how to actually extend these results to graphs that are beyond graphons, and how to really sort of treat, how to say, more modern complex systems applications. All right, so in the broader goal, it's a little bit of a community program, at least in the community where I'm from, sort of applied nonlinear dynamics, is that you want to build a dynamical systems theory where the sort of discrete mathematics of networks is sort of visible and interwoven with the sort of dynamical systems aspects that are sort of more classical. And this talk contributes to a certain sort of epsilon aspect of this entire broader community program. All right, so many society challenges are sort of at the heart, are driven by network processes, and they're at the heart best described by network dynamics. You could think about epidemics, not only COVID, but also something like Ebola or the flu or HIV or many other sort of infectious diseases. I sort of put here a nice New York Times article that I found a good quote in. So US deaths near 100,000, that was in May 2020 for COVID. But I think the subheadline is even sort of really nicely put. They were not simply names on a list, they were us. So I think that this is important motivation for scientists to really look at network dynamics models and see, can we do good predictions that help us to basically survive? Yeah. Political dynamics is intrinsically a network dynamical process. It's pretty well understood now that social media and the interaction, how people sort of discuss and debate about politics, induce major shifts in society and of vital importance for the 21st and even like a couple of 100 years ahead. So we need to understand how these processes really work, and we currently don't. We have some idea, but we don't really understand them at heart dynamically. Then, machine learning and neuroscience, sort of either the artificial or the sort of real neuroscience, is intrinsically a network process. And, it's not only a process where you think, okay, I can maybe put this in a computer and get an output, like in engineering. This is quite common to a certain extent. But there's also a mathematical issue to this. Can you, for example, for machine learning algorithms actually prove something about their validity, their robustness? Can you understand how these algorithms really work? And the same is true for neuroscience. Can you derive good models of the brain? Because it's usually very difficult to study the brain in its entirety or just sort of do it by purely experimental means. So would you let a robot lawyer defend you in the context of machine learning? Well, I mean, if you have enough math to know that the robot lawyer is reasonable from your point of view, maybe. But if you think, okay, I'm pretty sure I don't understand what this algorithm is doing, you would probably say no. Yeah. And so then there's, of course, this engineering aspect to network dynamics, where, for example, the internet would be a good example, but also a sustainable power grid for sort of renewable energies would be an example, where we build huge engineering structures that might be prone to attacks, that might be prone to breakouts, and sort of, you know, disturbances that sort of really could bring down one of our major or some of our major communication or supply means. And again, this is effectively a network dynamics problem. So really, you need reliable mathematical methods to capture all these dynamical systems processes on networks. And you know, we have a certain understanding of each of them, but I think math can really contribute here. So then you would argue, well, there are many classical network dynamics models already. Why don't we rely on these? Yeah. For example, in principle, the n-body problem from classical celestial mechanics is a network problem. There are bodies that are linked by gravitational forces. Gas dynamics is a network problem. The classical Ising model in magnetization, classical branching processes are effectively processes that run on a tree. Classical coupled oscillators like mechanical pendula. These are all properties, or well, these are all sort of processes which have some underlying properties that are a little bit, how to say, simplifying the whole analysis. Yeah. For example, you could physically embed many of these processes very easily in sort of spaces that you're very commonly acquainted with in your intuition, like R3, for example, where you put all the bodies in, and then you say, okay, how do these bodies move in R3? Yeah? Or they're sort of very structured, like the Ising model classically was posed on a lattice. Yeah? So you put a lot of structure into the graph. Or like for branching processes, they are tree-like. You have a very natural sort of graph that's simply, well, not simple, but relatively simple to analyze. Yeah? Or you just assume everybody is talking to everybody, like classical coupled oscillator models do. And then it's also becoming a lot easier because somehow the influence of one guy on the other guy, one oscillator on the other oscillator is really quite equal. So, but really, if you think of a network coupling of these more sort of complicated processes that I've put up that are some of the big challenges of the 21st century, you know, take an example. Take, for example, the spreading of an epidemic and the spreading of the information about the epidemic. And these processes are obviously coupled, and they are obviously happening on networks, and you now want to model them. Well, first of all, can you physically embed them? Well, probably not. I mean, maybe the people who spread the epidemic, yes, but even then with long-range connections and airports and all sorts of other fast transportation means, maybe this is difficult. And all the information, well, how do you embed that in a physical space? Not easy. Are these processes on a lattice? Well, not really, because, you know, clearly there are sort of long-range connections. There are some short-range connections. There's not a very regular structure in the connections that you just have always a fixed number of neighbors. There's a lot more heterogeneity than a lattice. Are they tree-like? Well, locally, maybe for a certain sort of initial part of the epidemic, the process is pretty tree-like. Yeah, it can be well described by branching trees. But then after a while, if you go away, if you're in a regime where you're away from this initial outbreak, then it's not tree-like. The same is true for information. Maybe in the beginning, it's a bit tree-like, but then at some point, there's much more sort of, you know, loopy stuff to it than just a tree. What are these processes all to all? Well, no, well, clearly not. I mean, not everybody is able to infect everybody, in principle, because there are some limitations how people can move, and information not easily spreads from everybody to everybody. You just have a finite amount of information that you can digest. So all to all is out. So in principle, you see that many of the classical tools developed in the context of like something like the n-body problem, gas dynamics, or the Ising model, these processes are, how to say, they are good and helpful, and you should start from them, but we need additional mathematical methods. Okay, so let me give you a paradigmatic model that already appeared several times in this mini symposium, which is the Kuramoto model, which I will use throughout my presentation, where I will go from a classical Kuramoto model to a more networked Kuramoto model. So Kuramoto had this idea to study synchronization, and also Art Winfrey was involved, and many other people in the sort of 70s and 80s tried to study synchronization phenomena. And now I will try to do an experiment that most likely, since I'm trying this the first time, will massively fail, but I will try it anyhow. So what we will do is we will try to do a live Zoom experiment on synchronization. So I will change to the gallery view. I will change to the gallery view, and I ask you all to sort of unmute, well, not to unmute, but to sort of make your cameras come up and try to do this experiment with me on synchronization, on actually trying to synchronize waving. So please, if you are so kind, maybe turn on your camera if you are willing to take part in the experiment. So the idea is you do this sort of waving motion slowly, and you just do it at your own frequency. Okay, just do it and put it in the camera and do it at your own frequency. Don't look at the others for now. Do it at your own frequency. Yeah? Just your own frequency. And then now, since you're doing it at your own frequency, try to synchronize somehow to the others. Slowly. Yeah, we are getting there, see? After a while, we have actually managed to somehow at least partially synchronize, right? Very good. Thank you very much. You can turn off your cameras again if you want to. So this was a quite, I think, how to say, interesting experiment. And what it showed you is that somehow you synchronize with the others without there being any sort of master conductor, or you actually being able to look at all the pictures at the same time. Right? You didn't look really at all the pictures and try to process all the information, try to process where do I have to go. It's far too much information. You only focused on one or two people or on one part of this gallery view of Zoom, and you try to somehow adapt your face to this sort of subset, this little sub-community in this heterogeneous network of coupled oscillators. Okay, so what's the classical Kuramoto model? And well, in the classical Kuramoto model, synchronization is even easier to analyze because there is no network coupling, but everybody is talking to everybody. So the classical Kuramoto model says, okay, you have oscillators that are on a circle. So we have the phi j's that are on a circle, and that's the phase of the j's oscillator, sort of the, where you are in the waving cycle, basically. And the k is the coupling strength. That's basically how much you pay attention to all the others. And Wj is your intrinsic frequency. That was your initial waving frequency that you adapted. And usually the natural assumption in Kuramoto models is that you assume that somehow over all these oscillators, let's say there are n oscillators, these frequencies are randomly drawn, just for simplicity, by some density. I will not use this much during my talk, but it's just, it's a classical assumption in this business of coupled oscillators. And usually what you do is when you want to analyze this model is you look at the order parameter. The order parameter is this R, which is sort of this prefactor before this complex exponential, which is just a weighted sort of phases effectively. Yeah. So the R gives you, if the R is small, then it says, well, all the phases on the circle are sort of roughly spread around, and you have very little synchronization. If the R is close to 1, this means all these phases are very much moving in unison. So this was at least sort of, we were probably in this diagram where the order parameter was relatively high. We were somewhere probably up here where there was a sort of a chance that we synchronize. And you can actually analyze this ODE model. By the way, prime is a time derivative, I should say, just to be clear. So these are ODEs coupled and with values on the circle for each oscillator. And if you actually vary the coupling, there's a sort of critical coupling that you can calculate, that above this critical coupling, these oscillators start to partially synchronize. And the higher do you in turn the coupling, then at some point you're getting very close to sort of complete synchronization, meaning you're getting to this area up here where R is, say, relatively close to 1, where almost all the oscillators are bunched up in the same phase. And this is a good toy model because the dynamical system it describes on the level of finite n is extremely nice. Yeah, so it's a very nice bounded right-hand side with a relatively simple nonlinearity and a still relatively simple structure for finite n. But you can generate in a sort of quite amazing complexity in the fact that if you really look at the sort of changing the coupling strengths, you get this sort of coherent behavior of synchronization. So as such, it's a good sort of base model for network dynamics. So here's the sort of natural generalization. These are what I would call Kuramoto-type models. So what do I mean by Kuramoto-type models? I mean models where you have sort of intrinsic dynamic for every node. X could be in some phase space, doesn't have to be on the circle. It could be in RD, it could be in some other sort of space that you like, usually some Banach space. Yeah, but also finite dimensional spaces are equally good. Yeah, you can put any space you like. And then there's a general coupling function that tells you how does sort of an oscillator J process the input of oscillator K, and how does that how does that XJ sort of in this more general Kuramoto-type model, how does that XJ, that node J, process the incoming information from all the other nodes. And how does it do it? Well, it sort of takes a weighted average over a coupling function over all the other inputs. And for today, I will assume for simplicity that, you know, F, J, and G are as nice as you like. Lipschitz continues, probably even better if you really need to. And you assume that there's sort of sufficient symmetry and there's no self-interaction. So assume that you don't get sort of an input in this Gj of G of xj, xk from yourself, but you only have your own intrinsic dynamics, and then you have, you know, no sort of self-reinforcing term. Yeah? So the question is, what is a mean field model? And I want to explain this in this classical Kuramoto-type model, how to get a mean field. We already seen this a little bit, what mean fields are. So let me try to derive how you get at mean field models. What's the idea? Well, the idea is, well, for simplicity, by the way, I will do this now for no intrinsic dynamics. So suppose you don't have an intrinsic phase, all you're doing is sort of drifting around the circle. And to assume also for simplicity, just for algebraic simplicity, that I remove the parameter and the k is equal to 1. But okay, so basically we are asking these sort of ODEs, what can you say if n becomes large? Can you simplify them? Can you find a reduced equation that somehow describes these xj, this particle or this node? And the idea is, well, under certain circumstances, you might be able to do that because I put deliberately only one coupling function g here. Meaning, like every node feels sort of the same types of inputs to a certain degree. So you could think, okay, maybe there's sort of a typical node. And if you just study the behavior of this typical node, I sort of understand the whole system behavior, because there's the sort of high degree of symmetry that every node sort of averages over all of their neighbors in the sort of same fashion with the same sort of coupling function. And indeed, this is true. And mathematically, to be a bit more precise, the idea is, well, you hope that the right-hand side of this differential equation, if n tends to infinity, you can somehow replace by an integral. So far, so nice. And you also assume that there's some sort of typical measure for one particle that you can put so that there's actually a sort of closed form integral equation that you get by sort of replacing the sum. And that would be the equation in some sense that mu is satisfying later on for a typical particle. Yeah. So, or even better, if mu is not a measure, you could also hope that maybe there is a density, so that it's absolutely continuous, for example, with respect to Lebesgue. And there is a density u that is sort of the density that's evolving, or the sort of probability of, you can think of it like a probability of finding a typical particle at the position x at time t. Yeah? This is sort of the mean field description. And indeed, you sort of want a typical particle or a typical node. And if you do that formally, you end up with such an equation, which sometimes is referred to as characteristic equation, but that's not closed because you need an equation for the mu, which is sort of the typical location of that particle. Yeah? So the idea is you want to analyze this ODE, or it's basically an integral equation in some sense. I should have probably written integral equation, but effectively it's sort of an ODE type equation because there are no partials on the right-hand side. And you view this ODE type equation as a sort of characteristic equation for a PDE. So if you do that, then you get what's called the Vlasov equation, or a mean field Vlasov equation for this measure mu. And indeed, if you do that formally and you rewrite that this is sort of the characteristic equation for a PDE, you get a first order PDE in space. Well, and that's the form of this form where you actually have sort of just the gradient in X, and you have the vector field from this particle is just intrinsic inside this gradient dot product. Yeah. And okay. If you plug that in, that would be a nice way of doing. And if for a density, it would look even nicer. You would have an evolution of a sufficiently nice, hopefully sufficiently regular function. And if you would describe or could derive an evolution equation for u, and you could prove that this whole procedure is correct, then u would just be sort of describing the distribution of the evolution of a typical particle. And you wouldn't have to study the system on finite level n, which could be really difficult for many, many particles, but you could go to a mean field limit and study the equation for u, and you would know what a typical particle does, and then you would know about the behavior of the system. Indeed, if you go back, you would then hope that sort of this diagram here, you could derive from this mean field Vlasov equation, because on the left here below this synchronization threshold, you would assume that the typical particle just sort of spreads out, Whereas here up there, you would assume that the typical particle is sort of very deterministically synchronized at a certain position. So here you would think that the solution for this density is sort of uniform, roughly speaking, whereas here, when it's synchronized, you would assume that this is a very peak density, yeah? Because there would be a more like deterministic position of a typical particle, where here all these particles spread out, which means the solution of that Vlasov equation should be like more like a uniform density or distribution. Yeah? Okay, fair enough. And indeed, classically, this works. The way to prove this, I cannot go through this in detail, but let me at least indicate how the proof works. The proof is actually quite smart. What you do is you look at what's called the empirical measure. So you take your finite end system of all your particles. You place basically deltas at where your particle is in space, yeah, in the phase space that you have chosen, for example, S1 or RD or some other space. And then you just take an average over where all these particles are. And then you hope that sort of this average over all these particles indeed correctly describes, as n goes larger and larger, this sort of position of this typical particle. And indeed, and this is sort of the goal, you try to prove that this empirical measure, as n tends to infinity, at least over a finite time scale of the evolution of your dynamics, that this in some metric actually converges to some limiting measure, and this limiting measure satisfies the Vlasov equation. So indeed, the limiting measure mu here is indeed the solution of the Vlasov equation. Okay, very good. And this strategy was developed in the 1970s, 1980s. Probably the nicest papers I would recommend are papers by Neunzeit. There's also a paper by Dubrushin that is very well written up in a survey paper by, or a survey article or lecture notes by François Goltz from 2013. So there's lots of literature on how to prove this sort of empirical measure convergence. There are two key steps. Usually one is you have to select a metric. Yeah, so you have to select a metric on probability measures to do this convergence. People have done this in total variation. They have done this in Wasserstein. So there's different types of probability sort of distances that you could use. And once you have chosen a metric on the space of measures, then you need to prove that over a finite time scale, there's some sort of Graphons-type result that says, well, there's some constant that could potentially grow with t, but this constant is finite as long as t is finite. And on the left-hand side, you have the distance between the empirical measure and the solution of the Vlasov equation. On the right, you have actually the distance between the initial conditions for the finite system and for the Vlasov equation. If you then prepare the initial data that they are identical, then you know that indeed for, as n tends to infinity, you know that you get actually the right approximation result, that the empirical measure actually converges to the solution of the Vlasov equation. Okay. Very good. So this was without network coupling. So what about networks? So we have seen that this all-to-all coupling business that I have now, every guy is talking to every guy, like in the classical Kuramoto model, is simply not fitting for today's applications. So you need to think, okay, how do I stick in coupling in these models? Well, the way to stick in coupling is sort of easiest and probably the correct way of doing it is would to say, well, not everybody is talking to everybody, but there's some graph which has an adjacency matrix an on the finite level n, which is sort of zeros and ones for simplicity, say. And if there's a zero, these guys are not talking j and k, and if there's a one, j and k are talking. If there's a one entry for a, j, k, and this gives you, well, a very natural network variant for the Kuramoto model. So and then you think, okay, why not just take the mean field limit again? If there's sufficiently enough coupling, even if it's heterogeneous, but if sort of sufficiently talking to each other, you could still hope that there is maybe a typical particle or potentially several classes of typical particles. Yeah, maybe not just one class of typical particles for the homogeneous case, but maybe there are sort of typical classes of particles even in a heterogeneous system. For example, I don't know, 100 classes or 10 classes. That evolve sort of similarly, and you would assume that then you still get some sort of limiting Vlasov-type equation, but that is tricky because now you're having an additional limit object that you need to take care of, and the limit object is the limit of this graph. Yeah, because before you didn't care too much. Yeah, the limit object of this graph was so simple that the graph structure wasn't even visible really, because everybody was talking to everybody. They were just all ones, and all these ones drop out. You never see them. But if these ones do not drop out, you need to think about carefully, how do I interpret the graph limit? Yeah? How to do that? So, well, the natural intuition would be you use graph limit theory from discrete math, and there's lots of people who worked on this. I mean, there's a nice book by Laszlo Lovac, also lots of papers by Szegedi and Jansson and many, many others. So these dots are probably hundreds or thousands of papers. Yeah. So I don't want to, there's no sort of claim to completeness in my literature references here. I'm going over 5 different sort of research fields. So I really have to refer you to the papers to be sort of more complete in terms of literature references. But the ideas in graph limit theory, they're sort of very dense graphs where you sort of have superquadratic growth of the edges in comparison to the vertices. So these are relatively dense, and people have understood that in these cases, quite often you can use Graphons. There's sort of this intermediate graphs where you're in between linear and quadratic growth when you compare the number of vertices and the number of edges. And there's also sparse graph where they're sort of sublinear, where you really sort of have a very slow growth when n gets larger of the number of edges in comparison to the number of vertices. And there, usually what you need to use is a classical theory called graphings, which are designed for sparse graph limits. Roughly speaking, these graphings give you quite ugly measures on the unit square that can represent the limit graph. But this is for how to say maybe broadly for an analyst, this is somehow not super satisfactory, and I will explain you a little bit why. Yeah, so that you somehow, there's currently no really good tool, or at least since a couple of years ago, there was no good tool to deal with intermediate graphs and sparse graphs from a purely analytical viewpoint. But there is one for dense graphs, and I want to briefly review this. So if you're sort of joining now and you haven't seen previous talks where Graphons were mentioned, so here is now my 5 cents on Graphons, if you wish. So dense graphs and Graphons. So think about the following picture. If you have never seen this, think about a growing adjacency matrix. And then think about just the adjacency matrix having zeros and ones. The matrix is growing, and think about the pixel picture of this adjacency matrix where you put sort of a function that is 1 on the unit square, where you have a 1 in the entry in the matrix. And if you refine the matrix, you just split up these squares into smaller squares. And if you refine it again, then meaning that you grow the graph, then you split up this again and into finer and finer grids. And at some point you are asking, okay, to what limiting object does this pixel picture on the unit square converge to as n gets larger? That's sort of one of the base ideas of Graphons. Yeah? So the Graphon, as a definition, would just be a symmetric and measurable function on the unit square into 0, 1, which sort of can represent on a finite, as well as we shall see on an infinite scale, certain classes of graphs. So it's a natural object that you would hope could be used in graph limit theory that you could transfer to use in PDE theory, yeah? Or network dynamics, if you will. Yeah? So key ideas is, well, as I said, you can, if you want to represent a graph on a finite level, you can represent it by a graphon by just taking this pixel picture, sort of meaning that you sort of take the unit square, you chop it up into a grid, and then you just put zeros and ones where they are adequate, meaning where you have a connection, you put a 1, where you have no connection, you put a 0. So just in the jth, kth sort of subpixel, you put that in. And then you can view these functions as step functions on the unit square, and you're asking in some topology, for example, in LP, the classical case would be, of course, p is equal to 2, whether these pixel pictures, meaning these graphons on a finite level, converge to something. Yeah? And this you could try for many different classes of graphs. So you could hope that there might be a representation for many graphs in terms of graphons that you describe them on a finite level by a graphon, convert them sort of to this pixel picture, and then see where this pixel picture converges to in LP as n tends to infinity. Okay, this is nice and elegant. There are examples. Yeah, you can take nearest neighbor graphs, and then you get a sort of very nice graphon that sort of has a band structure, because meaning if you order it correctly, only sort of there's a band of nodes that are sort of black, because this is only the nearest neighbors, and then you get a banded matrix, and this banded matrix converges to something very nice in the limit, namely again a banded sort of function. You could do random graphs. So you could say, put the probability of a pixel having 0 or 1 just being equal to p. This would be the Addish-Renyi model. And you can show that indeed in the limit, this converges to a graphon, that the graphon is just a flat function p. So again, this is reasonably nice. and you somehow have a representation of graphs in terms of graphons. And then you can use this. So you assume that the coupling is actually now given in terms of a graphon, meaning the AJKs are actually sampled at every level n from a structure that is given to you. So you take a graphon, you assume that AJKN is representable via this graphon. And then you look at the interaction term formally, like we did before. So you assume Wn converges to some W. Yeah, this means to a function on 0, 1 cross 0, 1. And then you just take the same limit as we did before. So you take the right-hand side sum. Here I've written it with G, so there should be a G here instead of the sign. So I've written sign here, but of course trying to do the general Kuramoto model. So it's a typo. There should be a G of phi k, phi j here if I write it like this, or I write the G just as a sign. Yeah, either way would be correct. So this was just some intermediate sort of, unfortunately, slightly incorrect typo. So if you then take the limit of this right-hand side, then you see you would expect that instead of the normal integral, there would be, an additional integral term that would be sort of convolving effectively with this graphon limit. Yeah? Because that is what the limit would be. You take a sort of step function, and then you take a limiting, step function that is in this sort of sum. This would converge, at least formally, to an integral. And indeed, this idea can be made precise. So for the normal Kuramoto model, so when G is equal to sign, you can actually make this precise, and you can prove that the mean field Graphops limit PDE, this was done by Chiba and Medvedev in 2016, the paper appeared in 2019. Yeah, you get a limiting equation where there's an additional integral. So there's an integral over the frequencies, which is this R integral. So this is just the distribution of the frequencies. So the alpha you can just discard for now. If you want to do it a little bit simpler, just discard in your brain the alpha, which is the distribution of the intrinsic frequencies of the oscillators. But then the other important integral is this new integral, which is basically convolving the density of a typical particle with a graphon. Yeah? And then you got a limit PDE. That's already great because you can already treat some heterogeneous type network structures, and you can understand how heterogeneity in the network actually translates into mean field behavior and translates into stability and translates into all sorts of stuff on the mean field level for this PDE. Yeah? But somehow, I always was sort of bugged by the fact when this graphon business came up in sort of, say, the early 2010s, roughly speaking, I was slightly bugged by the fact that there's two things you would want to do. You would also want to treat sparse graphs, and particularly many sparse graphs and sparse graphs where there are graphings or intermediate graphs. Yeah? And these you can often not very well treat by graphons. And if you try to incorporate sort of the classical discrete math techniques from graphing theory and also classical graphon theory, actually, then it's mostly combinatorial tools like homeomorphism densities, really counting arguments. And it's really quite difficult to put these limit arguments into a good context for us here in the analytical business of deriving an integral differential equation. So the intrinsic problem is that graphons are sort of integral operators. This sort of means that you can view them basically as having a sort of an operator that always comes with an integral and always is sufficiently regular with respect to Lebesgue measure. And I could never really fully make sense of. I had this sort of intuition that probably one should make this more general, but it seemed very difficult to me to do all these combinatorial things analytically. But luckily, I sort of was rescued by this paper in some sense, which once it appeared on the archive, basically the next day I started working on this because I was really convinced that this is a good technique. So Backhaus and Szegedy proposed that you can view all sorts of graph limit objects, meaning the sort of graphons, graphings, and also all sorts of intermediate graph limits via operators. So they really say here, we present a new approach to graph limit theory that unifies and generalizes two most well-developed directions, namely dense graph limits, or LP limits, which is basically graphons, and Benjamini-Schramm limits. So these are graphings, even in a stronger local global setting. And I was like, okay, this must be good, because if it's operator theory, this is something I can deal with. I can use operator theory and measure theory and analytical techniques to put now limits of graphs into my theory of dynamical systems. And I can treat much more general classes. And I checked it first formally, meaning I just plugged and chugged and sort of manipulated the symbols. And indeed, you can check by manipulating the symbols that things are consistent, and you do expect the Graphops techniques that Backhaus and Szegedy developed. So they call their new sort of notion that I will present on the next few slides, they call it a graph op, so a graph operator. And indeed, you can show that you can do network dynamics using Graphops, so you can put the operator into the mean field dynamics. So this is very nice. I've written that out, and this is in this paper from a couple of years ago. So now, what are these Graphops? How does this work in practice? So how do you get these new combinatorial techniques from discrete mathematics that converted combinatorics into operators and measures? How do you get this into differential equations? So the really smart idea that I want to briefly sort of explain that Backhaus and Szegedy had is, why even bother with operators? Well, they noticed that this is the best view of graphs of different sizes. Yeah. So the idea is this. I think this is quite smart. So I wanted to present this. They cooked this up. So you view the AN, it could be the adjacency matrix, but it could also be some other operator on a finite graph, like the graph Laplacian or some other type of object that derives from a finite graph. You view this purely as an operator. You take a vector so that you can just act on by this matrix. Yeah, so let's say it's an n cross n matrix, then you get another vector. So you got two vectors now, v and a and v, and this basically represents the sort of domain and the range of this operator acting on a particular vector v. And now to convert and compare different sizes n, the idea is not to look at these vectors purely, because if you would only look at these vectors, this would be n dependent. If you make n larger, you would have different size vectors. This would be very inconvenient to compare different graphs. How would you prove that there's a Cauchy sequence of convergent graphs? You couldn't really. I mean, you could try, but it gets very complicated. So the smart idea is you sort of coarse grain this in the correct way, meaning you look at that you sample from this n cross 2 matrix of v and a and v uniformly at random. That's basically a measure theoretic sampling of the action of this operator an. And this gives you a family of measures that depends on the vector. You can scale that to have measures on 0, 1, well, cross 0, 1, effectively. That it's not on R2, but it's on a unit rectangle. So you can scale these measures. And if you scale the vectors v, you basically scale the measures. Yeah, and then you can compare measures instead of like combinatorial objects. And I was like, this must be useful for PDEs and mean field limits and network dynamics, because now graphs and the associated graph operators and the way they are treated and the way convergence is looked at, and they call this action convergence in this paper of Backhaus and Szegedy, is purely always on a measure theoretic level. Yeah, so the old arguments of Neunzeit and Dobrushin are on a measure theoretic level, and now also the graph limit arguments are purely on a level of comparing measures, yeah, or comparing operators, if you will. Yeah, and this is great. So operator viewpoint is very helpful. So what are Graphops? What is the operator viewpoint associated to this sort of theory? So the idea is you fix a probability space. And you can think of this omega as the space of nodes. I will give examples in a second. Then the associated sigma algebra, and you fix a measure. For example, if this would be a sufficiently discrete set, you put a uniform measure. If this would be an interval, you put Lebesgue, for example. So you can choose the measure. And then you fix some P and Q, and then you consider the usual LP spaces, and you look at operators that have a well-defined norm from P to Q. And you define an operator from L infinity to L1 that has finite norm in the usual sense is called a P operator. And if you have a positivity preserving and symmetric P operator, this is called a graphop. Basically, it's the abstraction of a graph. Why it's the abstraction of a graph? Let's look at an example. Yeah, so maybe I should, well, the example is on the next slide. Maybe I should go to the example, but on the next slide, there will be an example why this is a natural way of abstracting the notion of a graph. Let me first make a few remarks. First remark, well, it's actually a theorem, is that once you have such a graphop, that's a symmetric positivity preserving P operator on the probability space, you can represent this by a family of fiber measures. So you can represent this by a family of fiber measures. This is effectively, if you look at it sort of, through the lens of analysis, this is sort of a variant of the Reed's representation theorem. It says there's an operator and it has a family of measures that Reed's represented. Yeah? And you can interpret these fiber measures as actually sort of, if you interpret this omega as the vertices, so we will do this in an example on the next slide, you interpret this space omega as the space of vertices, you interpret the space omega cross omega as the space of edges, and you interpret then the fiber measure as actually local connectivity of a certain vertex. Yeah. So the fiber measure describes you the sort of local connectivity, and it gives a representation of the graph via a measure. Yeah? Let's do some examples. So this is quite interesting. So here are some examples. Why are finite graphs representable that way? Okay, so take an adjacency matrix, for example, symmetric, non-negative, and say zeros and ones for simplicity if you wish. And it acts on V, like by matrix vector multiplication. You can phrase this in terms of Graphops by just picking this omega as the discrete set from 1 to n. You say, okay, and take the usual power set for the sigma algebra, and you take the uniform measure on this discrete space. And then you say, okay, the V, which is my vector, I can interpret as a function from omega to r, because, well, it takes an index, and after you plug in the index to a vector, it spits out its entry. Yeah. And then, well, how does this AN act as a P operator on this space? Well, it takes matrix vector multiplication. After matrix vector multiplication, it's a new function, and you evaluate that new function at an index, which is the index I, which is nothing else but taking the matrix vector product and taking the ith element out of the resulting vector. So basically, graphs are P operators, quite naturally. And also Graphons are P operators. Yeah. So you take a non-negative kernel. Again, you could think of making it sufficiently nice by adding additional requirements, but suppose it's just non-negative and sufficiently regular. And this acts on F. Well, how does it act on F? Well, you first take omega is now, since we are sort of a continuum limit, you take just 0, 1, which would be a space of nodes. Usual Borel sigma algebra, take the Lebesgue measure, for example, and then the graphon would become just an operator, a P operator that acts on a function, and it's just convolution effectively, or integration against that function over 0, 1. Yeah, so of course you can then put requirements that, typically you put P is equal to 2 is equal to Q, but you could also put all sorts of other graphons you can incorporate in this sort of graph op language. So there's also graphs of intermediate density that are more complicated than normal matrices or graphons. So here is an example. It's the spherical graphop. This is a graph of intermediate density. Okay, let's look at that graph. It's again, you can interpret this as a graphop. Yeah, so you take as a space the unit sphere. Yeah, and then you say, okay, take the usual Borel sigma algebra and take the uniform measure over the unit sphere. And then let's suppose we describe now this graphop via its fiber measures. So just for practice, if we do that, we just sort of put a uniform measure on all the z, so that z is actually in the sphere, and the index z is actually a vector. You can view the z as a vector, and this vector has to be perpendicular to all the z tildes. So geometrically speaking, you fix a z, and the guys that are connected to the z are all the other vectors that are orthogonal to the vector that defines the z. So you just take the origin, you go to the z vector, you check all the other vectors that are orthogonal to it, and these are the guys that are connected to it. And remember, the fiber measure gives you the connectivity. And this gives you a well-defined graphop, except that this graphop is neither sort of super sparse, nor it's super dense. It's actually of intermediate density. Yeah, you can check that this is an intermediate density graphop. And it's very difficult to represent such an object by a graphon or by a graphing. You would be, a little bit at a loss. And this is what Backhaus and Szegedy realized. Okay, so now how do you do very general mean field limits? So how am I doing on time? Maybe I should quickly check. So yeah, do I have about 10 minutes? I guess that 5 to 10, something like this.
Yeah. You have, in any case, you have 4 minutes and you can take some time. From
okay. So I will probably take around 8 minutes to finish. I think this should be all right. Then I'm eating a bit into the question time, but I hope that's okay.
That's fine.
How do you do this now? How do you incorporate graphops into mean field limits? Well, you say, all right, suppose now the AJKNs, they are not really necessarily sort of being given by a graphon, and they are sort of given by a more general graph object that you're expecting in the limit as n tends to infinity. How would you assume these AJKNs, when n tends to infinity, how should they show up now in the Vlasov equation? Well, there are two viewpoints. As I said, there are Graphops as operators, or there are Graphops as fiber measures, because that's an alternative sort of structure that describes the Graphop. And let us just use a formal analogy for now. Before, we were basically having an integral that was like integrating the density that we are trying to solve in the Vlasov equation against a Graphon. But if we replace the Graphon now by an operator, then this integral goes, and this operator A infinity, which is the graph op limit of a graph, which due to Backus and Szegedy, we know in many cases this graph op limit does exist, because you can use action convergence to prove that many graphs of sparse intermediate and full sort of large density do have actually well-defined graph op limits. It's one of their main theorems that they prove in their paper. And you take this limit object and then you include it into your mean field PDE by saying, aha, this operator is acting on U abstractly, and you get a new variable, because this Z is the variable that now sits inside your omega, your 0, 1, and it parameterizes effectively the different types of node structures that you could have. So this Z variable sort of takes care of the heterogeneity in the network by saying, if it's all-to-all coupled and very uniform, the Z drops out. You don't have anything because everybody is talking to everybody. If you just have two node classes, there would be a discrete sort of dependence upon Z. If you have more complicated dependence, well, then there would be a much more complicated family of coupled differential integral equations that describes the mean fields of multiple typical particles that are co-evolving. But okay, if you have this viewpoint of an operator where this A acts on U, you could abstract. You could say, aha, there's also the additional abstraction that you could represent this operator that's the limit by fiber measures. Yeah, so basically Reed's representation theorem. If you do that, you get another integral, but now this integral is not a Graphon type integral, but it's an integral over your sort of node space, your vertex space, omega, and it's actually you're integrating against the measure. You are integrating against the measure that you are getting as the limit of these fiber measures. And this now is amazingly consistent, because what you see is now all the objects are as nice and as analytical as a person in dynamical systems could hope for. They're operators, they're measures, and you're looking at measure theoretic convergences and at operator theoretic convergences. So you have hope that you can prove also rigorously the existence of a Vlasov equation under certain conditions. Yeah. Of course, you can also think, okay, there might be densities, then you could do it with a density. Yeah, this is also fine. So here is sort of the statement, at least, of the theorem. Proofs are quite long. So here are two sort of theorems and two ideas how you could get at these sort of Vlasov mean field PDEs. So first, think about the Graphop viewpoint. What we have shown is existence, uniqueness, continuous dependence, and discrete finite dimensional approximation of a mean field Vlasov PDE for certain type of Kuramoto models via a Graphop viewpoint. Yeah? So there's still some stuff in the paper that we are working on. So there's some sort of classification that we need to still add. So this is still in sort of revision, you could say. And then we are using Graphons in this paper to approximate Graphops via harmonic analysis techniques. So the natural idea was, okay, we have operators that we want to represent. Why not reuse the existing results about Graphons, approximate my graph op by a sequence of Graphons, and then show, okay, as long as I can do this approximation in a suitable sense, and we use some nice harmonic analysis techniques to do that, then indeed you get a well-defined Vlasov equation. And you can do this sort of keeping track of suitable norms, effectively. Yeah? But then you think, okay, what if we want to generalize that and we want to get rid of Graphons completely, because they are still in this first theorem that's jointly with Mario Skokas, there's still sort of this dependence on the Graphon viewpoint to a certain extent, at least. Yeah? If you want to do that, you can just purely switch to a measure theoretic viewpoint, and instead of operators, you can look at fiber measures. And in this paper, which is joined with Chuang Chu, we actually have recently proven that you again get existence, uniqueness, and continuous dependence and discrete finite dimensional approximation for mean field loss of PDEs for Kuramoto-type models by actually using measures theoretic viewpoint and adapting an original sort of idea of Neunzeit. It's called the Neunzeit in cell method. And there we need to keep track of carefully how to treat certain types of metrics, meaning how to actually do this argument that I said in the beginning. You need to show sort of a Grunwald type inequality in a suitable metric. And we need to keep track of the growth of this metric when we do the comparison of the empirical measure in comparison to the limit measure that satisfies the Vlasov equation. And indeed, there we can show that you could sort of discard this sort of additional intermediate approximation step, which might be constructive and helpful for applications in many cases, but maybe from a very abstract viewpoint, you might want to have something that is sort of purely measure dependent in some sense. All right, so we indeed do get closer, an epsilon closer to our initial goal to update classical mathematical techniques from mean field limits from homogeneous or highly structured or lattice type systems to heterogeneous systems by using these ideas from converting discrete mathematics into operators and fiber measures, and we are able to prove Vlasov equations for limits of Kuramoto-type models. And this is my summary, so it's my last slide. So as I said, many classical methods exist. Classical methods need major improvements for heterogeneous complex networks. And we can actually get Vlasov PDEs in the limit that incorporate very general classes of graphs. And these operator and measure theoretic viewpoints of graph limits are key. So this is our link from discrete mathematics to basically functional and real analysis, and then sort of to dynamical systems. And the result are quite novel, I think, equations that are well posed and that approximate finite particle systems in a sort of completely new and heterogeneous fashion. And here's some of the references to the papers. We can also probably do this for higher order structures. I wanted to also mention this paper that Toby presented on Monday. So probably we can adapt what we have done here also to sort of higher order interactions, because the framework is not really limited to what order the interaction has. And you can download all these papers and the links and everything from my website. And now I would like to thank you for really paying so long attention over these 50 minutes. Thank you very much.
Thanks a lot.